So one session on basic fluid dynamics, in fact the fluid dynamics that we are digressing on is an extremely simplified version of fluid dynamics. We are looking at one-dimensional flow, that too steady state and streamline, and results primarily Bernoulli's theorem guiding almost all the related results. We spoke of what is referred to as a streamline, and along a streamline how we could preserve the value of P by rho g plus V squared by 2g plus h. We defined that as the pressure head, the dynamic head, and the datum. We also looked at an application of Bernoulli's theorem where we computed the velocity of efflux root 2gh for a container that is filled to a height h, and the reaction force associated also if the orifice of efflux was not too small but sizable. How do we deal with that? And based on the geometry we could find the volume flow rate through that, etc. Also the reaction force, right? Did I in my previous class also mention to you two containers levels of liquid unequal, joined by a very narrow tube, narrow orifice of area of cross section small a. Did I speak about the flow rate from one to the other? Velocity of flow would be root 2g into the difference in the levels, h1 minus h2, right? Now, what we want to be able to do is figure out what eventually happens and how long it takes for that to happen. Eventually, the pressure here and the pressure here would get equalized, preventing further flow from the left container to the right container. That's going to happen when the levels of the liquid get equalized in the two containers. That means the final scenario would be when the levels are, say, h each. Right? Now, if A1 is the area of cross section of this vessel and A2 is the area of cross section of this vessel, what's the total volume of fluid in the two vessels put together? A1 H1 plus A2 H2. Is the total volume of the fluid in the two vessels put together? No, this is negligible. This is negligible. This is a very small opening and a very short tube. We will ignore the... And the total area, total volume here is going to be A1H plus A2H. That means A1 plus A2 into H is the total volume here. And the two volumes must be equal. Right? This H is the final common height in the two vessels. And I want to be able to find out the time it takes for this equalization. Right? Now, an intermediate state starting from here, H1 decreases and H2 increases. Right? H1 decreases and H2 increases. An intermediate state would be the following. Where this is small h1, this is small h2. This is an intermediate state during the flow from the left container to the right container, right? Now at this stage, the velocity of efflux from the first container to the second container, V, is going to be root 2g into h1 minus h2. That's the velocity of efflux from container 1 to container 2. The volume flow rate at this instant is going to be the area of the orifice, small a, into V. That's going to be the volume flow rate from the left container to the right container. So the volume flow rate at this stage is going to be small a into root 2g into h1 minus h2. Yes or no? I'm seeking to compute the time it takes for the levels to get equalized. This is the volume flow rate in this intermediate stage. And since h1 minus h2 varies from, see, this h1 minus h2 is a variable, it's not a constant, right? Initially, h1 minus h2 is actually capital H1 minus h2. And finally, h1 minus h2 becomes 0, isn't it? So h1 minus h2 varies from capital H1 minus capital H2 to 0. It's a variable, delta H. You might want to call it delta H, right? So I want to find the time it takes for delta H to change from h1 minus h2 to 0. Now, if this is the volume flow rate across this small orifice, cubic meters per second at this, then at this instant, let's say this is an intermediate instant t, h1 is decreasing with time, So, the rate at which h1 decreases is minus dh1 dt. Why minus? Because h1 is decreasing with time, dh1 dt is a negative number. So if I put in a minus sign, that will give me a positive number. That's the rate at which this height is decreasing with time at this instant, right? So rate at which the volume changes in this container, rate at which volume decreases in this container is going to be A1, the area of cross section of this container, into the rate at which height decreases. Rate at which height decreases is minus dh1 dt. That's the cubic meters per second decreasing in this container at this instant. Yes or no? Right? And that must be equal to the rate at which the volume is decreasing here. That must be equal to the rate at which it's flowing into the second container through the orifice. This is the orifice side of the story. This is container 1. Right? Now, in this case, h2 is increasing with time. Now, the rate at which h2 is increasing with time is dh2 dt. So, the rate of increase of volume of this container would be A2 into dh2 dt. These many cubic meters per second is increasing in this container at this instant of time, which must be equal to this. That's essentially a continuity equation. That's essentially a continuity equation which is equating volume flow rate throughout, right? So, the rate at which this volume is increasing is A2 into dh2 dt. Yes or no? Do you all understand this? This is the volume flow rate through the orifice. This is the cubic meters per second decreasing in this container. This is the cubic meters per second increasing in this container at this instant of time, and they must all be equal. That's because of a continuity requirement, right? Now, this is the physics of the problem. We need to take care of the mathematics. This is the physics. Let's now take care of the mathematics. Let's find the time it takes for h1 minus h2 to go from capital H1 minus capital H2 to 0, right? So let's gracefully address this issue. So, if I use these two, then dh1 dt is minus a by a1 into root 2g. Can I write this as delta h? The difference in the intermediate difference in the heights? Delta h is a function of time. This is delta h, right? So into delta h. Can I say this? Using these two, dh1 dt is a by a1 into this. Can I say this? Now using these two, dh2 dt is a by a2 root 2g delta h. How about it? Right? Now I want to make delta h, that is h1 minus h2, the subject of my integration. I want to make delta h the subject of my integration. Very clearly, I have delta h appearing fine on the right hand side. If I subtract these two, then this will become ddt of h1 minus h2. That means ddt of delta h. And then I'll have delta h all over the place without interference. Right? Yes or no? So, if I subtract these two equations, this and this, then ddt of h1 minus h2 is minus 1 by a1 plus 1 by a2 a times root 2g delta h. Yes or no? On subtracting these two, this is what happens. Yeah, please hop in. Or this is d of delta h, isn't it? This is d of delta h, right? Divided by root delta h. I bring root delta h below this. Is minus 1 by a1 plus 1 by a2, I write as 1 by a, say. I mean, loosely speaking, don't take me on face value. Like we have reduced mass, you want to call it reduced area only for internal consumption. A you can refer to for an internal consumption as reduced area. Like reduced mass, we had 1 by m is 1 by m1 plus 1 by m2. No, nobody calls it reduced area. Only in-house we'll call it reduced area, small, capital A, right? So only for algebraic simplicity, to avoid clutter, I'll write 1 by a as 1 by a1 plus 1 by a2. So minus small a by capital A root 2g dt. This is what transpires. Let me integrate both sides. All of this is a constant, will wriggle out at time t equal to 0. What was delta h? This was time t equal to 0. Delta h was capital H1 minus capital H2, the initial height difference. And let's say at time t equal to t, delta h becomes, or if I just want to find the time it takes, delta h eventually becomes 0. Or if I took t and delta h, I will get delta h as a function of time. This is what. But if let's say t is the time, which is the total time it takes for delta h to become 0, then these would be my limits of integration subscribed to. This is easy to integrate. You can supply the limits and you can obtain the time it takes for equalization of levels in the two containers. Not a result to be mugged up for sure, but this is how you deal with it. This is all that I wanted you to know. Is that okay or not? Yes. Oh, okay. ddt of delta h minus 1 by a root 2g delta h, right? How is this 1 by a1 plus 1 by a2 as 1 by a? That's my choice here. I call 1 by a1 plus 1 by a2 as 1 by a. Can you prevent me from doing this? It's almost a fundamental right that I have in mathematics and sciences. Can I not call anything as anything else as long as it's not blasphemous? A is a1 a2 by a1 plus a2. Now, can you accept this gracefully or gleefully? I mean, why am I calling it 1 by A? Okay, you call it 1 by B if you like. I will have no qualms. You want to call it 1 by B? Huh? No, it's okay, na? I mean, there was a clutter. Otherwise, I would have had to write A1 plus A2 by A1 A2. So I said, yeah, let's make it look a little dignified. That's all. Okay? Call it the goddamn area. I'm okay with that, yeah. Don't bother about the name. Like I said, there was nothing cardinal about the name, not the scientific community that has given it this name. I said only internally, let's call it like a reduced area. Because reduced mass, is M1, M2 by M1 plus M2. You might want to just call it like a reduced area, A1, A2 by A1 plus A2. Okay, don't bother about it. Just call it 1 by A. No, so that it becomes easier to write, yeah. That's all. Eventually, I know what A is. A is A1, A2 by A1 plus A2. Right here, I can plug capital A as A1, A2 by A1 plus A2. It would have just consumed more time to do that. But, you have more than offset the time I have saved by doing this. You have done the compensation. The two have, now I feel, I shouldn't have done this. Might as well have stuck with A equal to A1, A2 by A1 plus A2 and performed the last rites on this. What a sin I committed. All right. All's good? Huh? Now, hey, hi guys. I'm dealing with kids. Of course, another fact that I want to just make a very explicit mention of is, the equation of continuity, which is like, if there is a flow occurring in a small channel where the datum is not varying significantly, and if this area is A1 and the velocity of the fluid entering this area of cross section is V1, and when it leaves with an area A2, then equation of continuity means that there is no deposition or accumulation of fluid anywhere. All the fluid that is entering a given cross section is leaving that cross section. This is all that it means. That means at every point, the mass flow rate is the same. I mean, again, mass flow rate same also for an incompressible fluid would mean volume flow rate being the same. So we are talking of incompressible fluid. So the volume flow rate is the same. So equation of continuity is simply a statement on saying constancy of volume flow rate through any given cross section, right? So we have like V1A1, the volume flow rate through this, equals V2A2, the volume flow rate through this. That's the equation of continuity. Now, suppose there is a vessel and there is an orifice at the bottom, small orifice at the bottom, and there is a flow occurring. And the area of the orifice is small a. Now the velocity of a flux here at this area small a is root 2 gh. Suppose this is h, is root 2 gh. Now what happens is when fluid emerges out of this, falls down under the influence of gravity, then its velocity will increase, right? Suppose v is the velocity here, and at a depth x below this, let's say the velocity becomes v1. The velocity here was v. So now from here to here, it's free fall. So can I say that v1 squared is v squared plus 2gx under the influence of gravity? Under the influence of gravity, the square of the velocity at a depth x becomes v squared plus 2gx. That means as this stream jets out, the velocity increases. Now if the velocity increases, what must happen to the area of cross section? It must decrease. So there was a jet of diameter small, of radius small a, or rather of area of cross section small a here, then the area of cross section must be smaller here, so that the volume flow rates must be the same. See, what's the volume flow rate through this? For this jet emerging, small v into a at this instant. Now when this jet falls a height x, what happens to its velocity? v1. Now if v1 is its velocity and a1 is the area of cross section of this jet, if a1 is the area of cross section of this jet at this point, then the volume flow rate through this would be v1 into a1. a1 is this area of cross section, right? Yes or no? That's the volume flow rate coming out of this. That's the volume flow rate through this cross section, and the two must be equal. Yes or no? V is known to me. V1 we have computed, and V1 is more than V. V1 is more than V. So A1 must be less than A. So it tapers down. Right? The area of cross section decreases as the water falls, as the fluid falls freely under the influence of gravity. This cross section becomes narrower. This cross section becomes narrower because of increased velocity out of continuity considerations, right? There are times when during this free fall, velocities become significantly large. And velocities, when they become significantly large, the flow that was streamlined up to this point loses its streamlined character at a certain critical velocity. And therefore, there are times you would have observed that when water falls through a trap, then after a certain depth, it looks a little hazy because there is turbulence that gets initiated beyond a critical velocity. So that might happen if the velocity v1 becomes significantly large, then turbulence might result and the flow may no longer be streamlined or laminar, right? No, v1 is greater than v. That is fundamental, and therefore a1 becomes smaller than a. It's not a pipe, my friend. It's not a pipe. It is falling freely. It's not a pipe. There is a jet from this small a. There is a jet which is being released. Now I'm claiming that the area of cross section of the jet will decrease because the velocity under the influence of gravity is increasing. So the area of cross section of the jet which is being released at area small a decreases. This is not a pipe. Then sorry, how will it taper? No, that will not happen. Then there would be pressure variations. Again, along this, the datum changes. Then to compute the velocity, you would have to apply different considerations. If it's a pipe, then at the exit of the pipe, the velocity of a flux would be root 2 gx, not at the entry of the pipe then. Yes. Have you ever seen, just try it out, take a pipe and create a whole of area A, would you find some empty spaces in that pipe? Tell me, can that happen? No, that will not happen. It will consume the entire area available, right? If it's a pipe, then at the exit of the pipe, the velocity of efflux would be root 2 gx, not at the entry of the pipe. That will be the difference, right? Now, there are two applications that we very often talk of with regards to Bernoulli's theorem. One is an application where we measure the velocity of a fluid through a pipe. An arrangement of this kind. There is a pipe, not of a very large cross section, and there is a fluid flowing through the pipe, let's say with a velocity v. What we do is, we have an arrangement of this kind where a tube of this kind, an arrangement of this kind is attached to the pipe. There is a fluid of density rho naught flowing through the pipe, and there is a U-tube which contains a fluid. The U-tube which contains a certain fluid of density rho f. Now, how does this arrangement help us compute the velocity of fluid through this pipe? See, what happens is, this is small cross section, so volume flow, the velocity at every point is the same, practically the same. Now, when a sample of the fluid enters this pipe, this fluid is different from this fluid, right? When a sample of the fluid makes an entry here, when it strikes us, its velocity becomes 0, right? Now, if the velocity becomes 0, that means the pressure must increase. Commensurate with Bernoulli's theorem, if the velocity decreases, the pressure must increase. So the pressure here is higher than the pressure here if I imagine this point and this point. Obviously, at this point, velocity becomes 0. At this point, velocity is v, right? At this point, velocity is v. At this point, velocity is 0. So if the velocity decreases, pressure must increase to be consistent with Bernoulli's requirement. Consequently, this goes down. This level is pushed down because of greater pressure above this limb. This experiences greater pressure, and therefore this gets depressed. Consequently, the level of the fluid in the two limbs will become unequal, right? Let's say this point was 1 and this point was 2. The pressure here is because of pressure at 1, P1, right? The pressure here is because of pressure at this point, which is 2, P2, right? Yes or no? And P2 is more than P1, and therefore there is a difference in the levels. Let's say the difference in the levels that you witness in the two limbs is delta H, which can be measured. These limbs are calibrated. So you can measure the difference in the levels in the two limbs. Evidently, P2 minus P1, the pressure difference is because of this differential height. So that must be equal to rho f g into delta H. That's P2 minus P1. Now, between 1 and 2, right, outside this extension and this point where it hits, I can apply Bernoulli's theorem, right? So at 1, what's the pressure? P1 divided by, now the fluid, rho naught, P1 by rho naught G, plus V is the velocity of the fluid in this pipe, V squared by 2G. Now H is practically the same between 1 and 2. In fact, at all points in this cross section, H is the same because the cross sectional area is very, very small of this tube through which the fluid is flowing, right? So H is the same anyways on both sides. Now the pressure here is P2 divided by rho naught G, and the velocity becomes 0. The velocity becomes 0. Yes or no? Evidently then, V squared by 2G is P2 minus P1 divided by rho naught G, right? V is what we seek to compute. V that we are seeking to compute then is going to be 2 times P2 minus P1 divided by rho naught. Yes or no? Now what is P2 minus P1? P2 minus P1 is rho Fg delta H. Delta H is measured directly from the limbs. Delta H is measured directly from the limbs. This will give you the flow rate in the pipe. Flow rate in the pipe. This arrangement is called a pitot tube. It's called a pitot tube, which is essentially used to compute the velocity flow rate through a channel, right? Just by measuring delta H. Now rho F and rho naught are properties you are aware of, densities of the flowing fluid and this fluid, and you can compute the flow rate through this, right? Now you have another arrangement which is connected in series with pipes to measure volume flow rate, which through channels. An arrangement with 2 different cross sections which is connected in series through a flowing pipe, across a flowing pipe. Let me show you that arrangement too. Can I wipe this off? You're okay with this? An arrangement of this kind. It's connected in series with a pipe through which there is a flow occurring, and I want to be able to compute the volume flow rate. I connect this arrangement in series with a channel, with a view to compute the flow rate, cubic meters per second through the channel. All right. Now, it has a narrow portion which has an area of cross section A1. This portion has an area of cross section A1. It has a broader section of area of cross section A2. Now, when it is connected in series, if V is the velocity in meters per second entering this, and let's say at A1, the velocity becomes V1, the velocity of the flow becomes V1, and A2 at this cross section, which is greater cross section, velocity becomes V2. Evidently, we can preserve the flow rate across any given cross section So V1A1 must be equal to V2A2. Cubic meters per second must be the same out of continuity considerations. So V1A1 must be equal to V2A2, which is the volume flow rate. Which is the volume flow rate which we are seeking to compute, right? Now, A2 is more than A1. A2 is more than A1. So V2 must be less than V1. V2 is less than V1, right? Now, if V2 is less than V1, see, again, the datum is the same everywhere. So the potential head does not vary significantly across this cross section, right? So if the velocity here is smaller than the velocity here, then the pressure here must be more than the pressure there. So if the pressure here of the flowing fluid is P2 and the pressure here of the flowing fluid is P1, then very clearly V2 less than V1 would mean P2 more than P1. P2 more than P1, right? Yes or no? P2 more than P1? That means the pressure in this cross section is more than the pressure in this cross section. So now the liquid that is flowing through this will rise in this limb and will rise in this limb. But since the pressure in this cross section is more, it will rise to a greater height in this limb compared to this limb. Yes or no? Right? So it rises to a certain height in this limb, whereas it rises to a smaller height in this limb. Why? Because the pressure here is P1, the pressure here is P2, and P2 is more than P1. Therefore, the height above this must be more than the height above this. Yes or no? Right? Very clearly, again, if the difference in the levels observed in the two limbs is delta H, then the difference in pressures is because of this delta H. That means P2 minus P1 must be equal to rho G delta H. Must be equal to rho G delta H. Rho is the density of the fluid flowing through this. Density of the fluid flowing through. Now you don't have two different fluids. It's the same fluid which gets sampled into these limbs. Unlike the previous situation where you had a different limb in a different liquid in the U tube. In this case, it's the same. To accommodate the pressure difference, there is a differential height accommodated. Right? Now, what I do is, in this cross section, refer to S1. In this cross section, refer to this as 2. Between these 2 points, I can apply Bernoulli's theorem, right? So, P1 by rho G plus V1 squared by 2G. H is the same on both sides. Datum is the same. Potential head is the same. And that must be equal to P2 by rho G plus V2 squared by 2G. Now, if the volume flow rate was V, V was the volume flow rate, right? Through this channel. Not the velocity. Now, this one is the volume flow rate, cubic meters per second. V is what we want to compute. V is what we want to compute. Very clearly, I can transpose P1 by rho G on this side. P2 minus P1 by rho G. But P2 minus P1 by rho G is delta H. So this is delta H. Right? And V1 squared can be written as V squared by A1 squared. Right? This V squared can be written as V1 squared. V squared by A1 squared. Yes or no? V squared by A1 squared. And this V2 squared I can write as V squared by A2 squared. A1 and A2 are known to me. They are known entities of this arrangement, right? And therefore, from this equation, can I not solve for V, the volume flow rate through the channel, right? So this arrangement, again connected in series with channels, can be used to compute the volume flow rate through channels. It uses a single liquid, and this arrangement is called a venturimeter. It's called a venturimeter. Right? That's one time, and then it gets accommodated. It's one time it rises to that level. And then there is a steady state attained. Once it acquires that pressure difference, then it's the same volume flowing through this. It meets equilibrium requirements after a while. And again, even if it didn't, this volume is not like gallons of liquid. It's not like gallons of liquid. It's a small amount sampled there, and therefore there is no major loss of accuracy in making this assumption. This is, I've drawn it this big. The actual arrangement could be really small little thing, and these could be narrow channels, and the volume of the fluid that rises into these limbs is really, really small, my friend. So it doesn't affect the total working significantly. Okay. See, engineers work one way and scientists work the other way. Engineers will compromise a little bit of accuracy in the third place of decimal if it makes life simple. Physicists, on the other hand, would harp on getting the 20th place of decimal right and deploying mammoth effort to get the 20th place of decimal right, which may actually be no good. No, I'm not demeaning physicists. I'm only eulogizing engineers. Doesn't mean if you want to become physicist, you suddenly change your stance. Now, let me see, all along I've mentioned that we are talking of an ideal fluid. An ideal fluid, that is to say, it's incompressible and it is inviscid, non-viscous. Essentially, that's too much of an approximation. Incompressible is still all right, but non-viscous is actually not all right. When we are dealing with plastic flow through channels, which we deal with very often in injection molding machines and plastic fluid flow, then there is significant amount of viscosity that fluid that we are dealing with has. So in real life we actually have to deal with the with a property called viscosity, which makes it non-ideal. But then let's understand, what is this viscosity all about? Viscosity is a fundamental property of a fluid which not only depends on the nature of the fluid, it also depends on conditions like temperature and pressure, right? But let's say at a given temperature and a given pressure, what is viscosity all about? Let's try and quickly analyze viscosity. So imagine that there are two layers of fluid. Imagine that these are two layers of a fluid, very close, neighboring layers of a fluid. One has a velocity v, this layer of fluid has a velocity v. These are parallel layers. These are two parallel layers of a liquid or a fluid. And this has a velocity v plus delta v. let's say these two layers have different velocities. Now, essentially these two layers will interact with each other. What's the nature of interaction? At the molecular level, the molecules in this layer will attract molecules in this layer. The molecules will attract each other. The extent to which they attract will depend on the nature of the fluid, right? So one for sure, molecules in the two layers attract. When the molecules attract each other, it would to a certain extent impede relative motion between the two layers. It would to a certain extent impede relative motion between the two layers. The second thing that happens is the molecules here have a certain momentum. The molecules here have a certain momenta. The momenta of molecules here is higher than the momenta of molecules there, right? These molecules then exchange momentum. The momentum of this gets mitigated, it's partially given to this, and as a consequence, the momentum of this gets increased. The momentum of this decreases, the momentum of this increases. So there is an exchange of momenta. Consequent to the exchange of momenta, once again, the effect is depletion of relative motion. Relative motion once again would get impeded because the faster molecules will share their motion partially with molecules here. These will accelerate, these will retard because they have shared their momentum with particles here, right? So momenta get shared. So these are two effects, both of which would be pronounced and would simultaneously take place, and the impact of these two is to impede relative motion between the two layers, yes or no, right? And this effect produced because of these two consequences is actually viscosity. The property that the fluid possesses because it entertains these two properties is called viscosity. So viscosity is a consequence of these two properties. These two factors enable the existence of the property viscosity, which in turn impedes relative motion between adjacent layers of fluid. Right? Now, obviously you understand the momenta that the molecules have will depend on temperature. Alright, and the molecules will attract each other again. You know, temperature and pressures will become important in the overall game. Now, let us understand the model that supports viscosity, the mathematical model that supports viscosity. So, because of viscous motion, because of viscosity, this layer would exert on this layer a net force like this, a tangential force like this, and as a consequence of reaction to this force, this layer will exert on this layer a force equal and opposite drag like this, which is called a viscous drag. It opposes not motion but opposes relative motion, just like friction, right? It opposes relative motion. Now let's analyze the mathematics of viscosity. All right, But so far so good. In principle, this is what viscosity does as a property. Yes, please. Now, suppose there is a layer of liquid here. And this layer of liquid, let's say by some means, has a velocity u. And this layer of liquid is at rest. This layer, bottom layer of the liquid, let's say, is at rest. In the sense, you know, to achieve such a situation, what one could have done is, this could be like a fixed plate in a liquid, this could be like a fixed plate in a liquid, and this could be a movable plate moving with a velocity u. Therefore, liquid particles in contact with the lower plate will remain at rest. The liquid particles in contact with the upper plate will enjoy a velocity common with the upper plate. That's how you can achieve such a situation, for example. So it's not entirely hypothetical. Now, so between these two layers, let's say there is fluid. And say these layers are very close to each other. Let's say these layers are very close to each other. Say these layers are separated by a small distance y, say. Are separated by a small distance y, say. Now, imagine a fluid particle 0 here. Let me imagine a fluid particle 0 here which remains at rest. At some instant, let's say before all of it started, before I started to move this plate, there was a fluid particle on this layer right above this. Refer to this as 1. Refer to this as 1 fluid particle on the upper layer. And let's say y is small to begin with. Okay. Now, between 0 and 1, at this instant, let's say this was time t equal to 0. This was time t equal to 0. There would have been other fluid particles, let's say a fluid particle 2, a fluid particle 3, and so on and so forth. Right? Now, as this upper layer moves, right? One moves with a velocity u, whereas 0 remains at rest. Now, as you go from 1 to 0, the velocity of particles will decrease from u to 0 in a certain manner. Right? At the topmost point at 1, the velocity will be u. At this point O, the velocity will be 0. Now, an approximation. So the velocity from 1 to 0 decreases from u to 0. Now, if the separation between 1 and 0 is small, if y is small, then this variation of velocity is linear, is proportional. That means this is how the velocity varies. Topmost point, let's say, has a velocity u. Then the velocity becomes this, then the velocity of a particle becomes this, then the velocity becomes this, then the velocity becomes this, then the velocity becomes this. If y is small, these velocities of various particles from 1 to 0 will vary linearly. Means these lengths represent the velocities of various particles. This length represents velocity of 2, this length represents velocity of 3, say this length represents velocity of 4. So u versus this distance is a straight line. U versus this distance is a straight line. Variation of velocity along this is along a straight line. That's when we say u varies linearly with distance. It's a linear variation of velocity from the topmost point to the bottommost point. It's an approximation which is good if y is small. Right? But this may not always happen. So this is one possible velocity profile. So in this case, for every unit distance, u changes by the same amount. For a distance, say y. At 1 velocity is u, at 0 velocity is 0. That means the change in velocity per unit distance is u by y. The change in velocity per unit distance is u by y. So if it's a linear variation of velocity, then no matter where you select your unit distance, the change in velocity per unit distance will be u by y. However, if it was a non-linear variation, then the change in velocity per unit distance will not be u by y for every unit distance. It's going to be different, right? And so, in a certain sense, velocity varies with y, right? And u by y is called in this case, if it's a uniformly linear variation, it's called the velocity gradient. It's called the velocity gradient. It's the velocity gradient. Now, after a while, what is going to happen? In a small time dt, particle 1 will come to this point, right? Which is u dt. In a small time dt, particle 1 would have traversed a distance u dt. Particle 2 would have traversed this distance. Particle 3 in dt would have traversed this distance. Particle O would have been like this, right? So 2 comes here, 3 comes there, right? Now do you realize that this was a line that I imagined along the fluid, right? After a while, this line becomes inclined. This becomes inclined. We then say that there is shearing that has taken place in the fluid. The fluid has got deformed. Yes or no? Then the fluid has got deformed, right? Because the line joining 0, 1 has now got reoriented. Therefore, the fluid has got deformed, isn't it? The fluid has got deformed, isn't it? It's as if, imagine a solid and I take the top surface of the solid and I push it and the bottom surface remains the same. Then the solid gets what we call sheared. There is shearing then that takes place in the solid. So there is shearing then that has occurred in the fluid, right? Now, if this angle in time dt is d theta, then d theta would be a measure of what we call the deformation that has taken place. The deformation that has taken place in the fluid will be measured by this angle d theta. Yes or no? And this is called the strain. This is called the deformation or the strain. D theta is called the strain. Shear strain. D theta is called the shear strain. Right? Now, the rate at which shear strain takes place is d theta dt. Is the rate at which shear strain is taking place. D theta dt is the rate at which shear strain is taking place. Now, because of this shear strain, let's say the top layer will experience what's called a drag, which is a shear stress. The drag here is what's called the shear stress. The drag will be in this direction. In this direction, the topmost layer will experience a drag. A force opposing its motion will be experienced in this direction. This drag will be proportional. This drag will on the topmost layer will be proportional to the rate at which shear strain occurs. This actually is Newton's law of viscosity. This is Newton's law of viscosity. Not all fluids will enjoy this property. Not all fluids will enjoy this property. Fluids that enjoy this property are called Newtonian fluids. It's called rate at which shear strain takes place. Otherwise, if you don't like this name, call it abracadabra gili gili go jate raeti ho. One that enjoys this property. See, most fluids, what I can tell you is non-Newtonian fluids. For example, thermoset plastics, they are non-Newtonian. Plastics in general are non-Newtonian fluids. Water is almost for all practical purposes a Newtonian fluid. Yes. That's the drag. Now, if the topmost layer, if this was the topmost layer of the fluid, this layer on the top surface, if that had area of cross section A and it experienced a drag in this direction, then the drag per unit area is called the shear stress. The drag per unit area is called the shear stress. The drag per unit area is called the shear stress. That means viscous force. This is the viscous force acting on the topmost layer per unit area of the top layer is called the shear stress acting on the topmost area, right? Now, realize that u dt by y is tan d theta. Yes or no? Look at this triangle. U dt divided by y is tan d theta, right? Now, whenever theta is in radians and very small, then tan theta is approximately equal to theta. It's a good enough approximation. When theta is in radians and very small, then tan theta is approximately equal to theta. That's a good approximation. So d theta is obviously very small. So tan d theta can be replaced by d theta. And therefore, I end up getting d theta dt as u by y, which is the velocity gradient. Is u by y, which is the velocity gradient, yes or no? Ayush. That means also the total drag, the greater the area, the greater will be the drag. The greater the area, greater will be the drag. So drag is not only proportional to d theta dt, it is also proportional to the area of the liquid layer, area of the fluid layer. It's also proportional to the area of the fluid layer. If for the everything remaining the same, if we have the same d theta dt, but we double a, then the drag will get doubled. The drag will get doubled. So we can say the drag is like some constant into a into d theta dt. Constant into a into d theta dt. This constant will depend on the nature of the liquid. This constant will depend on the nature of the liquid. is a property of the liquid. The greater the value of this constant, the greater will be the drag. This constant therefore is referred to as the viscosity of the liquid. This constant is referred to as the viscosity of the liquid. And eta is the symbol commonly deployed. Eta is the symbol which is commonly deployed. Now, no, it's the drag between this layer and its immediately next layer. Yes, yes, it will experience, but I am holding it at rest by some mechanical means. If it was free to move, it would. If it was, let's say, two floating plates, and if I move this, then this will move. But if I am holding it, that means I am forcing it to be at rest, right? So it is experiencing a drag, but then that drag is opposed by some mechanical arrangement, right? Now, this drag then represented vectorially, let's say algebraically by a force F, is written as, now this d theta dt I can write as u by y. The velocity gradient, as we have established, is u by y. The velocity gradient is, now I put in a minus sign here, eta a u by y. Now what it really means is, this minus sign simply means that this drag, if u is to the right, then this f would be to the left. This is what it means, minus eta a u by y. If u is to the right, this f negative means f would be to the left. It's called the viscous drag. It's called the viscous drag. This eta, the SI unit of this is actually decapoise. Decapoise. Decapoise is the SI unit of this. A decapoise is like 10 poise. A deca means 10, but the SI unit is a decapoise. Eta is measured in decapoise. So if everything else is in SI units, then eta will be decapoise. Eta will be decapoise. Now, it may not necessarily be a linear variation of velocity all the time, right? The velocity gradient u by y that we have taken across this, which is like actually an average velocity gradient over a length y, may actually be different for different layers. The velocity gradient may be different depending on y. Between 0 and 1, the velocity gradient means what? The rate at which the tangential velocity changes in a direction perpendicular to it, right? These are the velocities, and the rate at which these velocities change in a direction perpendicular to this, that's the velocity gradient in the y direction. U by y is the velocity gradient in the y direction, right? Rate of change of tangential velocity as we move up in the y direction, that's the velocity gradient, right? Now, there are times when between these two layers, say this is the y direction, the velocity profile, this is u versus y, the velocity profile could be parabolic. It may not always be linear. The velocity profile could be parabolic in the sense, at this point 0, u as a function of y could be some ay squared plus by. If a was 0, then u versus y would be a linear variation. But if a is not 0, then u versus y is a quadratic variation, which graphically is a parabola. Then du dy, the u by y that you have seen would have to be replaced by du dy. The u by y, the velocity gradient that you see here then would have to be replaced by du dy if variation of u versus y is non-linear, right? So the viscous drag then is measured by minus eta a du dy. That becomes the velocity gradient in the y direction. And du dy you can compute as 2ay plus b. A and b would be constants known to you. So for any given y between this and this, you can plug in the value of y and you can obtain du dy for that y. Once you obtain du dy for that y, then you can obtain the viscous drag on a layer at that y. So for every single layer, you can obtain the viscous drag. F by A is the shear stress. F is the viscous drag. F by A is commonly designated by tau, which is the shear stress on any given layer. Which is eta du dy minus eta du dy, right? Now, some simple applications. Can I wipe this off? All's good? Now, suppose there is a layer of liquid of depth d, layer of liquid of depth d, of viscosity eta. Right? Now I have a plate. This is a plate on the top layer. You know, the top layer is a plate. This one is a plate of area A. And I want to move it with constant velocity v. I want to move it with constant velocity v. Right? I want to find out the power required to do so. I want to find the power required to do so. Right? Now, first of all, when it is moving with constant velocity v, first the velocity gradient, that means the plate here has a velocity v, point here has 0 velocity. So the velocity gradient is v by d is the velocity gradient. Yes or no? I'm assuming linear variation. If they have not given you anything on how velocity varies across y, then you will assume a linear variation. So you would assume total change in v divided by total vertical height as the velocity gradient. Clear? So this is the velocity gradient. So the viscous drag that it experiences is eta times A into V by D. That's a viscous drag to the left. So, you know, if I'd given it an impulse so that this acquires a velocity V and I let it go, then because of the drag, this plate will retard and its velocity will become 0. Therefore, if I have to maintain a constant velocity on it, I must apply an external force on it, right? And what must that force do? That force must exactly balance the drag so that the velocity is constant, right? So the external force that I apply on it so that it moves with a constant velocity must be equal to the drag, viscous drag that it experiences. So F then is like eta A into the velocity gradient, right? Now, if this is the force, which is a constant force, then the power associated with this force is going to be F into V, right? So the power associated with this force, these many watts, is what I would have to deploy on the upper plate so that it moves with a constant velocity. This is the external power required to overcome the drag. This is the external power required to overcome the viscous drag, right? Let me look at another situation. Can I wipe this off? Say there is a piston cylinder arrangement. There is a cylinder, and inside this cylinder there is a piston. Suppose this is a cylinder of radius r1 and there is a piston in it. This is a piston inside the cylinder, and the radius of this piston is r2, say. Cylindrical piston. Cylindrical piston. And in the annulus between the piston and the cylinder, there is a lubricant. There is a lubricant. These are very true mechanical engineering situations. Now, the lubricant will have a certain velocity, will have a certain viscosity. The lubricant will have a certain viscosity, right? What? Now, if this piston has to move down with constant velocity v, v is given to you. Why? In fact, have you ever seen those lubricants? They have goddamn high viscosities. Kitna gaada hota hai? Have you seen that? They are meant to have high viscosity. They are meant to have high viscosity so that they drag. Yes. They are meant to have high viscosity.
They have high viscosity. Shouldn't they, when we apply it, why does it become smoother?
No. We apply that because of some other reason. You know, Ayush, please visit me after class. In any case, lubricants are highly viscous. They are thick. They are thick, in fact. Now, when this moves down with a constant velocity v0, if I wanted to move down with a constant velocity v0, what viscosity of the lubricant must I select? What viscosity of the lubricant must I select? I want this piston to descend down with a constant velocity v0. Suppose the piston is of mass capital M, and I want it to move down with constant velocity v0. I have to make a choice on the lubricant. I have to make a choice on the lubricant. Now, in this case, the liquid particles in contact with the piston, the liquid particles in contact with the piston will have the same velocity as the piston, v0, right? And the particles in contact with the cylinder will have zero velocity? Yes or no? So, across this annulus, there is a velocity gradient, 0 to V naught. In this small thickness, we will assume linear variation, 0 here to V naught here on the piston, right? So, what's the velocity gradient in this annulus, right? The velocity gradient is V naught divided by R1 minus R2. That's the velocity gradient. Now, there is a viscous drag. What's the area that the piston has over which the drag is experienced? If L is the length of the piston, what's the curved surface area? 2 pi R2 L. 2 pi R2 L. So, over this 2 pi R2 L, it will experience a drag upwards. It will experience a drag upwards. What's the drag that it experiences? The upward drag that it experiences is going to be 2 pi R2 into L, which is the area, into eta, which is what I want to select, into velocity gradient, which is V naught by R1 minus R2. Now, if I wanted to have a constant velocity V naught downwards, then the weight downwards must balance the upward drag so that it has a constant velocity V naught. The weight downwards must balance the upward drag acting on the curved surface area of the cylinder so that it can move down with constant velocity, and you can compute eta from this. Now, one thing, it's a far-fetched thing. You may not have exactly that liquid of that value of eta, right? So when they are carrying out designs of cylinder piston arrangements in which the piston moves inside the cylinder, they can prima facie start with, these are all designs on paper to begin with, right? They know that they have to work around certain ranges of R1 and R2 which are allowed, right? They can change the geometry of the piston cylinder arrangement, but they can't force nature to produce a liquid of a certain viscosity, isn't it? So you may not necessarily be able to arrive at a liquid with viscosity as obtained by this. But then what you eventually do is you play around with R1 and R2, find the closest eta to that nature can provide, and then play around with R1 and R2 to obtain the available liquid, right? So then you find, well, eta you get as some value 0.1, say for example, but what is available is 0.15. So with 0.15, now you manipulate R1 and R2, R1 or R2, one of these, and obtain the required geometry instead of obtaining the required liquid. You know what I'm saying? So this is what they do in design actually. See, again, a lubricant is essentially meant to reduce frictional forces. So what we do is, suppose this entity is meant to slide over this without an intervening liquid, there would be large amount of friction and they will wear off. So what we do is, we place, to avoid the wear and tear, we place a thin layer of liquid between these two layers, because there would be play between these two layers, and that play, even though there is heat generated, it would be accommodated by increase in temperature of the lubricant, which can be taken. This is the objective of a lubricant. Smooth वाला बात नहीं होता है. Smooth वाला बात क्लास के बाद बताएंगे. Okay. Suppose There is a fixed plate here, FP. There is a movable plate here, and it has to be moved with a velocity v1. And there is another fixed plate here. This is a moving plate. Now this region could be filled up with a fluid of viscosity eta 1, and let's say separation between these two layers could be y1, whereas this region could be filled up with a liquid of viscosity eta 2, and separation between them is y2. What is the force required? What is the force required to move this? What is the force required to move this? Now this moving plate will experience drag from the upper fluid, will experience drag from the lower fluid, right? And say if A is the area of cross section of this plate, then because, now what's the velocity gradient in this region? V1 by y1 is the velocity gradient in this region approximately. The velocity gradient in this region is v1 by y2 is the velocity gradient in this region. So the drag because of the upper fluid is going to be eta 1 into A into v1 by y1 is the drag because of the upper fluid. The drag because of the lower fluid, eta 2, is going to be eta 2 into A into v1 by y2. That's a drag because of the lower fluid. Now this F must exactly balance this drag. This F must exactly balance this drag. So the power required is going to be F into V1. F into V1 is the power required. Got me? Now, let me very quickly and in brief look at flow of a fluid, a viscous fluid, through a pipe of uniform cross section. Flow of a viscous liquid, flow of a viscous fluid through a pipe of constant diameter, right? Now, see, if this was a pipe of constant diameter d, and this was the axis of this was the axis of the pipe, circular pipe. This was the axis of the circular pipe. Say the radius of this is capital R. Now, if the liquid flowing through this was non-viscous, then neither the velocity across this cross section would change nor the pressure would change. But because of viscosity, the pressure across the cross section does not remain the same. Pressure across one end to the other will not remain the same. In fact, there is, suppose this was my x direction, then there is change of pressure in the x direction. Pressure decreases because of viscosity. Pressure will decrease in the x direction. We have what is called the pressure gradient dp dx. Over a distance dx, pressure decreases by an amount dp, which is the pressure gradient. Gradient along the pipe. Now let's look at the net effect. What I would do is, see, again, you know, I can't conserve energy that simple. In a situation of this kind, even in a given cross section, the velocity will not remain the same. Suppose I imagined a cross section like this, which is this cross section. What I'm trying to obtain here is variation of the velocity across this cross section. Across a given cross section, what we'll see is that the velocity does not remain the same. This is what we'll see. So my objective is, in a flow through a pipe in which there is a constant pressure gradient, this again is an approximation. If delta P is the change in pressure over a length L, then delta P by L is going to be the pressure gradient. And P decreases with X. P decreases with X. So dP dx is going to be a negative number. dP dx is going to be a negative number. Because P is decreasing with X, so rate of change of P with respect to X is going to be negative. Now, I'm talking of a fluid flowing through this of viscosity eta. This is the pipe. And I imagine at a distance x from one end, a fluid element I imagine at a distance x a fluid element of radius small r. I imagine a fluid element of radius small r and of length, small length dx, small length dx. This is a fluid element in this pipe at a distance x, cylindrical fluid element and of radius small r. Small r varies from 0 to capital R actually. Now, on this, suppose the pressure at x is P and the pressure at x plus delta x is P plus dP. dP is the change in pressure. It's another story that dP will be negative because pressure is decreasing with x, so dP will be a negative number. This is the algebraic change in pressure, right? So now, on this fluid element, the lateral force is acting on it. There is going to be a force acting on this surface, left surface, which is P into pi r squared, right? And on the rightmost surface, circular surface, the force is going to be P plus dP into pi r squared, right? And there is going to be from the surrounding liquid, there is going to be a viscous drag to the left. There is going to be a viscous drag to the left acting on the curved surface of this element. There is going to be a viscous drag acting to the left, right? Now, for sure, if tau is the shear stress acting on the curved surface, tau is the shear stress acting on the curved surface because of the surrounding fluid, right? That will act in this direction, longitudinal direction. It's shearing, it's opposing relative motion, right? Then the drag because of the shear stress is going to be leftwards, and that's going to be tau into 2 pi r dx. Yes or no? That's the curved surface area of this element. That's the curved surface area of this element, and that's to the left. So let me call it negative. Everything leftwards, all the forces leftward negative, all the forces rightward positive. Then there is a force P into pi r squared acting to the right, and then this acting to the left. Right? This is the summary of all forces. And if it is unaccelerated, if this element is unaccelerated, velocity remaining the same because of continuity, right? Net of all forces acting on it is 0. To maintain a constant velocity, net of all forces acting on this element is going to be 0, right? Now,
Tau into 2 pi r into k. What's it?
tau is the shear stress because of that is force viscous drag per unit area. That's a viscous drag per unit area. And over what area is it acting? Over the curved surface, which is 2 pi r into dx. Dx is the length of this cylindrical element, right? Very clearly you can see p into pi r squared would get cancelled, and this gives me, again as you can see, tau equal to minus r by 2 dp dx. Yes or no? Shear stress as a function of r. dp dx I am assuming is constant, the pressure gradient. It's uniformly varying pressure, right? So, very clearly, where would the shear stress be a maximum? When small r is maximum? That means, on the outer surface, when small r is capital R, shear stress will be the maximum, right? On this, the shear stress would be the maximum, small r equal to capital R, and there is symmetry exhibited by small r. Yes or no? Whether you take small r above the central line or small r below the central line, it's going to be the same, right? So about this line, shear stress will demonstrate symmetry, right? And shear stress will vary linearly with r. Will vary linearly with r, in the sense, you know, along the central line, this is the central line, the shear stress is going to be 0 along the central line because small r is 0. And when small r is capital R, this is capital R, this is capital R, shear stress will be maximum, and then it decreases linearly to 0 here, right? And then this is at the lower surface, this is also capital R, shear stress will be like this and will linearly decrease to 0. From the outer surface to the central line, shear stress will vary linearly like this. Yes or no? Which means what you would expect in terms of velocity is shear stress being on the fluid elements on the close to the periphery being the most, you would expect smallest velocities here. And shear stress being 0 here, you would expect greatest velocities here, right? So you would expect a velocity variation 0 to a maximum at the central line. Along a given cross section, the velocity will be maximum along a central line. Yes or no? But let us figure out how exactly u is varying with r. How exactly u is varying with r. Yes or no? And do you realize that u is decreasing with r? So, if u is decreasing with r, du dr, which is the velocity gradient, in this case du dr will be the velocity gradient. Instead of y, you have the r direction. Instead of y, you have the r direction. So, du dr will be the velocity gradient in the r direction, and it's going to be a negative number. It's going to be a negative number, du dr, right? Now, shear stress at any given r, like we have just studied, is going to be minus eta times du dr, right? Minus eta times du dr, that's a shear stress, which is equal to this for flow through a pipe, where dp dx I am going to assume is a constant number. The pressure gradient I am going to assume is reasonably constant, right? Now this gives me eta du as half dp dx into RdR. Half dp dx into RdR. Yes or no? Eta du, this dr brought there. That's what we have. Right? dp dx is a constant number. The pressure gradient we'll assume is constant. And then I integrate both sides. This is a constant, so it will wriggle out of the integral sign. I integrate this. Yes or no? Right? Very clearly, one boundary condition that I know is when small r is capital R, u is 0, because particles in contact with the outer surface will have 0 velocity, right? So when small r is capital R, u becomes, u at small r equal to capital R will be 0. That's a boundary condition known to me, right? So when small r is capital R, u is 0, right? When small r is some small r, u becomes u. This will give me u at any given r. Yes or no? Right? Let us see what it turns out to be. This gives me like u equals 1 by 2 eta dp dx into, and this will become 4 when I integrate r. When I integrate r square by 2, so r squared minus r squared. This will give me u as a function of r. Very clearly, on the central line, small r is 0. Then I get the velocity on the central line by plugging in small r as 0 as 1 by 4 eta dp dx into minus r squared. Does it mean it's negative? No. Because dp dx is a negative number, it will take care of this minus sign and will give me a rightward u. Right? Give me a rightward u. So this u versus small r variation is a quadratic variation. It's a parabolic variation. That means across a given cross section, if I take any given cross section of this pipe, say this is the cross section, this is the central line, this is small r equal to capital R, the variation is going to be parabolic like this. This is the variation of u. U is 0 here and u is u max there along the central line at any given x. To maintain the flow, somebody would tell you what kind of a pressure gradient is required. So you have u as a function of small r. And it enjoys symmetry about the central line, because viscous or not viscous, there is no way to distinguish between layers of liquid above the central line or below the central line, right? So a parabolic variation across any given cross section is obtained. So I have knowledge of u at any given small r. Is given by this. This will be u a function of small r, right? Now, I want to be able to find the volume flow rate through this fluid. I want to be able to find the volume flow rate through any cross section. Any given cross section. What I do is see, let me look at a cross section at x. This is a cross section at x. It's going to be circular. This is a central line. Radius capital R, right? From this cross section, from different points of this cross section, fluid is emerging with different velocity because u is a function of r. So I can't say it's velocity into pi r squared. I can't say that. What I do is, let me look at this view of this cross section. When I look at the cross section from here, it looks like a circle of radius r, right? It looks like a circle of radius r with O as the center. right? Now, I imagine a small circular portion, circular strip, of radius small r and of thickness dr. Of radius small r and of thickness dr. Now, the velocity at a distance r would be u at r. So, through the shaded region, fluid emerges with a velocity u at small r, right? So, the fluid emerging through this shaded region, the volume of the fluid emerging through this shaded region is going to be u at r. This is practically all points are u at r on the shaded region, into what's the circumference of the shaded region? 2 pi r into thickness. 2 pi r is the circumference of the shaded region into thickness dr would be the area of the shaded region. Yes or no? Would be the area of the shaded region. So, velocity into dr. Yes or no? You know what I'm saying? So this will give me cubic meters per second through this shaded region. This is meters per second into square meters. Will give me cubic meters per second through the shaded region. This is the entire cross section. U as a function of r I can take from here and plug into that expression. The total volume flow rate would be sum of all of this, where small r changes from 0 to capital R. That's the volume flow rate through any given cross section. You don't have to mug it up, but you can integrate this by plugging in this. Very easy to integrate function. This is the only part to be integrated. This etc. as a constant will come out of the integral sign, and you'll be able to get the volume flow rate through any given cross section. Yes or no? That's fluid flow through a pipe in which the fluid has viscosity. Yes or no? Got me? All's good? You understand the basic ideas of viscosity? Nothing difficult about it? Stand back.